morning, everybody. Welcome to today's lecture. I don't know about you, I did not get too much sleep last night. And the reason is, of course, that the random variable we have been talking about, a World Cup winner, is finally certain. Very interesting. I would love to talk about what we just witnessed in terms of probability theory. But at the beginning, there's like 32 teams. For each of the teams, it's somewhat likely to win the World Cup, and then 16 teams are being eliminated, and there's like 16 teams left in the elimination stage. So the probability now concentrates on 16 rather than on 32 teams, and in every round the number of remaining teams is halved, so probability becomes concentrated ever more. And now we know, the probability of Germany winning the World Cup is 1. That is actually, we are certain now. And this would be very interesting to talk about this from the point of view of entropy, how entropy is something that measures uncertainty. So at the beginning of the tournament, we're rather uncertain, and with every stage, certainty increases. We could talk about this from the point of view of probability, but let's not dive into that. So, rather, let us briefly remind ourselves what we have been doing. We, in general, are talking about the problem of behavior programming for game agents. And we began talking about this by looking at fairly simple reactive behaviors, and discussed that more complex behaviors would probably need more information to be based on. In particular, contextual information, such as temporal context. What is going on, and not just like what is happening right now, but what is going on over a longer period in times. So, as one way of approaching that problem, we have been looking into the idea of Markov chains. And last week we actually discussed how Markov chains can be used to come up with decisions about what is likely to go on. If we have observations over a certain period of time, they may vary. Right? My behavior of, say, going from here to over there can look like this. It may also look like this. So sort of the data we have about what it means for me to go from here to over there can look different, but in both cases I have been going over there. And Markov chains are one way of reasoning under uncertainty. If we have different Markov models for different kinds of behaviors, and we have temporal observations about states a game entity is in, we can check which of our different models gives the best explanation for an observed sequence of states, and of course the one with sort of the best or most likely interpretation would be called the one that describes what is going on right now. Now, the issue is that in practice, we can, or we often cannot, I should say. It's actually the other way around. We often, and when I say often, I mean often, cannot observe the state a system is in. Well, I just said Markov chains would allow us to classify sequences of states, but quite often we cannot actually observe these states. Cannot observe the state a system is in, but what we can observe is what it does. So what do I mean by that? Let's remind ourselves of an example again. So here is a game map, and say here is a flag in a capture the flag game. and here is, I don't know, a health package, and here is ammunition, and I don't know, assume we were an artificial game agent belonging to the team that is on the attack, so we sort of enter the enemy base here, and we observe, somehow that is possible, an enemy player to move like this. And maybe one of our teammates has also entered this area here, is engaged in combat, and then we observe like the enemy player running around the enemy flag, and all of a sudden we observe this, and then we observe this, stuff like that. The point is, what we can see here is what the opponent does, but not what state is it in. For us as cognitive beings, this is easy to interpret in terms of, guarding the flag, running for ammunition, returning to the job, guarding the flag, running for health, returning to the job. So when I am talking about this, me as a cognitive human being, I immediately begin to abstract this enormous amount of information of, lots of, say, two-dimensional location vectors or two-dimensional direction vectors of this enemy opponent. When I want to summarize what is going on, I talk about 3 states or 4 states the system's in. So here it could be guard, run for health, run for ammunition, and return. Right? These are abstract ways of talking about what is going on here. These are summaries of sequences of lots of observed two-dimensional location or movement vectors. We see that, but if we were a computer program, we don't see that. All we see, all we have access to is actually like this location data. And the question is, would it be possible to infer more abstract states from that? And if we could do that, could we then continue as we did with the simple Markov chains, where we were observing the states directly, to classify what's going on here? And scenarios like this, so once you see it, it is obvious that this is a very common occurrence in game AI, but in many, many other areas of applied artificial intelligence or applied pattern recognition or machine learning, this is also the case. Right? The most famous example is the problem of speech recognition, where the stuff we observe are acoustic signals, and sort of the hidden states are the words that are spoken. So for an automatic speech recognition system, it does not see the words directly, but does see the acoustic signal and sort of has to abstract from the signal like what kind of states that could be. Once we have the states, the words that have been spoken, we can actually use sequences of these states to infer what is actually being talked about. Right? Once we have the words, we can check for sentences. Okay, so these are the situations where hidden Markov models shine. And yeah, last time we have already looked into the notion of hidden Markov models, and I will briefly summarize what we found or what we learned about, and then we have to speed up because we have to sort of come to the conclusion and solution of all of what we have been talking for the last couple of weeks, and I have to do 2 lengthy computations, And I have to speed it up because at the end of today's lecture I have to discuss the survey, right? So, in brief, right, what we found last time is that a hidden Markov model is something very similar to a Markov chain, where we have a graphical model like this, certain dependencies between random variables x1, x2, say up to some xt. In addition to what we learned when we talked about Markov chains, a Markov model has a second set of random variables. And those are called the observations. So we have O1, and that depends on state x1. And we have O2, and all the way up to OT. Right? So basically, two sets of random variables. The first one are the state variables, state, so x1 up to xt. And the second one are called the observations or the data. I'll use data because it's a shorter word. The data, O1 all the way up to some OT. Now, in all of what we are doing here, we assume the simplest case, that is to say a discrete state space. So these random variables that we call the state are assuming values in a discrete set S, which, I don't know, contains up to m elements, say S1 all the way up to Sm. State 1, state 2, state m. Now, since it is a discrete set, countable set, instead of state 1, state m, I could just as well call this 1 up to n. All right, I hope you agree on that. And I do not have to carry around the s with me, I just number these things. The observations are elements in another set, let's call it O. And this can be anything. This can be anything. For instance, in the example we just discussed, the observations would have been two-dimensional location vectors. But again, this can be really anything. It can be numbers, can be strings, can whatever. Vectors. Usually it is vectors, but these are things we can actually measure. This can be whatever we can measure. And these things we do not observe, but would love to infer from what we observe. Now, and this is the graphical model representation of a hidden Markov model. And then, given what we have been discussing so far, we can actually write down, just from looking at the model, the joint probability for all the random variables we are dealing with. And this is, of course, so the joint probability for the system, I know, assuming state variables x1 and x2 and x3 up to and xt, and then observation 1 all the way up to observation t. So this is the joint probability for all the 2 times t things we are dealing with here. Looking at this, we see that it factors as the probability, so the state variable x1, times the probability of the observation x1 given state x1. This is what this says. And now, sort of this repeats. So times, let me have it running from k equals from 2 up to t. Now we have the transition probabilities here, and that is to say p of xk given 1. And again, these emission probabilities, P of OK given xk. And if we look at this equation, we can already make out the 3 sets of parameters that define a hidden Markov model. So we have 3 sets of parameters. The first one is the transition probabilities. That is to say that we have this xk is I, given that xk minus 1 was j. We talked about this last time, it's an assumed time homogeneousness, so that could be abbreviated as aij. Don't ask me why it's called A in the context of hidden Markov models. When we talked about Markov chains, that was a P for probability. This A is a probability. It's just another name for that. Now, if we collect that for all the M states we are dealing with, this is to say that we are actually dealing with a whole matrix. Right? These are lots of numbers, aij. If we collect them into a matrix A, we find that this is an M by M matrix, where again M is the number of states we are dealing with. So this matrix is the first parameter of a hidden Markov model, and of course it contains lots of numbers. This is the first set of parameters we are dealing with. The second set of parameters is somewhat more abstract. This refers to the, so these are called the emission probabilities. Refers to this probability of observing an observation O, given that the model is in a certain state. Let's make it. If I was precise a minute ago, I'll have to be precise right now. So for each of the states, and we have M of them, this I can range from 1 up to M, we have probably a different probability of observing a certain output. So in our example, with the guarding of the flag in the capture the flag situation, say if we had a state that is called guarding the flag, then it is more likely to observe these vectors that would indicate this running up and down, then it would be to observe these vectors sort of running to the health package. Right? So depending on the state we are in, the probability of observing whatever we can observe might be different. Now, as the observations can be anything, and usually they are vectors, these probabilities are somewhat more involved. Right? These are actually probability densities. So this is a function, a probability density function, for instance the Gaussian. Each of these states could have its own Gaussian density defined over, I don't know, say the vector space of the two-dimensional vectors. Right? These could be Gaussians. And of course we have M states, so maybe we have up to M different such functions. And they are called Bi of O. This is to indicate that this actually is a function. So we call it Bi, and has an argument O. It's just the probability of observing O in state I. And of course, this is a set where I ranges from 1 to M. This is the second ingredient in a hidden Markov model. It's more involved than the first one. And the third one has to deal with this here. Right? This, we have now talked about this, and this here actually is sort of this. We've talked about the state transition probabilities, we have talked about the emission probabilities, this occurs here and here, but we have not talked about this, but this is also, as we can read from the equation, a crucial ingredient of the equation. So the third set of parameters is the initial state distribution, that's how it's called. So this is the probability of observing random variable x1 in state I. And this is called pi I. This particular number here, this probability is called pi I, and so we actually have a vector pi, because we have this for all the random variables, all the states. So this is an m-dimensional vector, and of course it is a stochastic vector. These are probabilities. They have to sum to 1, have to be larger or equal to 0. So this is what defines a hidden Markov model, and for what we are going to do today, I assume that these things are given. Of course, in practice, we would have to get them somehow. We would have to, somebody would have to provide us with these many parameters. Right? These are large sets of many different numbers. They have to be determined somehow, but we will blissfully ignore this problem. We just assume that they were there, and now are going to ask the question, what can we do with such hidden Markov models? So therefore, just to wrap this up, a hidden Markov model can be modeled as a tuple with 3 components. The first one is this vector pi, the second one is this matrix A, and the third one is this set of functions B. Right? If these things are given, if somebody has provided us with this vector, with this matrix, and with this set of functions, we could call this a hidden Markov model. And this is usually called lambda, don't ask me why. Now, I said we assume that this was given. But let me just briefly tell you the whole story. So, like, this is not, where does it come from? Like, how do we actually get the pi, the a, and all these functions b? Here's the story. I'm not going to write it down because, for the sake of time. We are dealing with a certain problem domain. In our case, it's game AI, game behavior, programming and recognition. Now, we define for ourselves a set of patterns we are interested in. For instance, the pattern of guarding the flag in a capture the flag game, and maybe the pattern of attacking the enemy base, and maybe the pattern of returning to the home base. You know, these things have to come from somewhere. Somebody has to say, okay, there are a couple of things we want to recognize. Once that has been defined, for instance, in speech recognition, we know we want to recognize words. Right? So we define a number of words we want to recognize. In the context of game AI, we define a number of abstract behaviors, complex temporal sequences we want to be able to recognize. Once that is defined, we need training material. So, in the context of game AI, we would have 100 gamers sit down playing capture the flag, and we would record what they are doing. Once we have all these recordings, somebody would have to label the recorded data. Would have to say, oh, from recorded frame 212, to 516, what the player did was attacking the enemy base. Right? Somebody would have to say from here to here it was that behavior. And then from, I don't know, in another recording that would be from frame 215 to 312. You see the length of these things can be different. This is the challenge in temporal pattern recognition. Somebody would have to label the data. Now, we have a lot of examples for what it means to attack the enemy base. Right? So there's lots of sequences of different lengths where we know that this sequence of recorded data describes the behavior of attacking the enemy base. We use these sequences, these many training examples, to train a hidden Markov model for recognizing attacking the enemy base. And the algorithm for training is called, training is called the Bauckhage algorithm. We are not going to look into that. But this algorithm, like once we have fed numerous examples into it, will run for quite some time and then produce a vector pi, a matrix A, and all these functions B. They will be determined automatically. All we have to do is to fix the number of states, say 12 or 200 or whatever. It's the only parameter we have to provide to this algorithm. The rest will be done automatically. This is interesting because we only provide the number of hidden states, but we don't say what they are. The algorithm figures that out automatically. So ideally we would verify what the training step did. And so we would have to verify what kind of states have been automatically uncovered. What kind of hidden states have been identified in the data we provided for training. So to that end we would again pipe a lot of exemplary sequences into another algorithm, and that one would produce the most likely sequence of states given the trained model. This is called the Viterbi algorithm. We are not going to look into that one, but after sort of these two stages, the results of this stage can be used to refine the learned model or models if need be. Once we have done that, we now have a couple of hidden Markov models, each of which is a model of a different behavior, a different abstract behavior. And therefore, in the application phase, we are interested in recognition. We are interested in the problem. Now, once we have all the hidden Markov models and the game is going on, and there is lots of temporal observations going on, what is going on? What is it the last 100 frames represent? And to recognize, we are dealing with the problem that we, given a sequence of observations, say O1 up to OT, so a lot of them, T could be 100, could be 1,000, right? So at the current point in time, the last 1,000 observations of what the enemy did. The next point in time, the last 1,000 observations of what the enemy did. This is given. We want to know what is going on, and this is the following problem. We have to determine the hidden Markov model that gives the best explanation of what is going on. I have to P in front of you, right? We asked the question, so we have trained a couple of hidden Markov models, each representing a different behavior. Now we observe something and we have to ask which of the models gives the best explanation of the observation we have. And this model would be called lambda star. We know lambda star, for instance, we have three models, guarding, attacking, retreating. In the current situation, guarding would have produced the largest probability here. Then we'd say, okay, what the enemy is currently doing is guarding. All right, and the question is, how do we do this? How do we compute lambda star? This is what we are studying today. How to compute this problem here. And this is, of course, the question basically how to compute this. Right? Because once we know how to compute this for one of the hidden Markov models, we can do it for all of them and then just go for the argmax. So how to compute the probability of a given sequence of observations for a certain model. And if we just were to know how to compute the probability of a certain sequence of observations, we can of course do it for all the models, right? So this is what we're interested in. In order to answer this, we have to be able to answer this. So in all fairness, in what is to follow, I would have to carry around this lambda with me, right? But I am so lazy, so I will focus on this problem. I assume we have just trained a single hidden Markov model, and I just want to know how likely a sequence of observation is given this single model. So instead of carrying this around with me all the time, I will compute with this one. Right? But it's obvious that if we know how to do this, we can do this for all the different models we have. Once we have done this for all the different models, we can actually answer this question. So this is the story. And in answering this question, we will finally learn and see and have an epiphany why we are so fond of conditional independence. So today, everything will fall into places. Let's see how that goes. Yeah, and this is a triumph of science again. Like this was a breakthrough. Now let's be, in order to appreciate what we are going to study later on, let's start with a naive approach. So, naive approach. We are interested in computing this expression, probability of an observed sequence given a certain hidden Markov model. I will from now on write this in a different way. I will write probability of O1 colon T. We are computer scientists, we should be used to that notation. This is just because, you know, all this dot, 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 T, whatever. This here is supposed to mean O1, O2, ON, all the way up to ON. Right? It's just an abbreviation. Yeah, this is something that is not part of the set of model parameters we have, right? We have the initial state distribution, we have the state transition probabilities, and we have the emission probabilities, but we do not have this. This is not part of our model. So how could we compute this? Well, one idea is to consider this as the result of a marginalization step. And by that I mean we could imagine this probability of observing a sequence of O's, observations, to result from the following marginalization. X1 sums from 1 up to m. Recall that the states are just called 1 up to m, not state 1, state 2. It's 1 up to m, the first state variable. We have to sum over all its possible configurations. And then we have to sum the second state variable from 1 up to n, all the way up to the tth state variable from 1 up to m. And I said it's a marginalization, so we have this sequence O1 to t. Let me be precise here. All the observations, 1 up to t, and then x1, x2, all the way up to xt. This is marginalization, right? We talked about this, so we have a joint probability of lots of O's and lots of X's, and we sum over all the X's. We marginalize over all the states, and the result is that. This is what we talked about a couple of lectures ago, when we learned about marginalization. Why would we do this? So let me again introduce a different notation for that. And this is again laziness. So this is the same as, from now on, sum x1 colon t p O1 colon t and x1 colon t. Right? This is just the same as this, but I am so lazy, I don't want to write all these sums all the time, and I don't want to write all these x's, so I am abbreviating this, but this is exactly to mean this. Right? Now, the very interesting thing here is that whenever we are given a joint probability, we might be tempted to apply Bayes' theorem, and this is exactly what we are doing here. So we can rewrite this joint probability where we have to marginalize over all possible sequences of x, no, not n, it's a t. We can write this joint probability as the conditional probability, where we have these observations conditioned on the states times the probability of the states. Right. Let me call this one 1. I don't know if I'm going back to this, but we can agree on that. Right? In particular, here you can see an instance of the trick I told you about. So we have lots of variables, but somehow I have sort of reduced this into 2 symbols, and with these 2 symbols you immediately recognize the structure of Bayes' theorem. Right? But of course, each of these things here is actually a long sequence of variables. Do not forget that. All right, why would we do this? Why would we do this? Because we have now cast the problem we are dealing with in terms of stuff we are given. Let me just show you that these things and these things can be inferred from the model parameters we have. Because we have that this joint probability x1 up to t. Let me, for clarity, write it like this. x1, x2, all the way up to xt. Right? This, looking at the structure of the hidden Markov model, we know that this joint probability is, of course, has to respect our graphical model times the product where k ranges from 2 up to t, p of xk given xk minus 1. But these numbers are part of our hidden Markov model. These are in the initial state distribution vector, and this is matrix A. Like, these are the elements of matrix A. So, in trying to compute this probability of observing a certain sequence, which we by marginalization can write like this, we have sort of found that this part here is actually can be computed given our Markov model, our hidden Markov model. Now then, what about this here? I'll erase it right now, but we are now concerned with this term in the marginalized. So let me, again, so we have the probability of 1 up to t given a certain sequence of states, and to be precise or clear, I'll just once write it like this, OT given x1 up to xt. This is another probability we would have to know in order to compute all of this. Do we actually know it? Do we know it? And
emission probabilities, like
pardon?
those are emission probabilities.
Hmm?
You're using emission probabilities
Yes.
to obtain this.
Yeah.
And the square of t objects.
Pardon?
If you distribute it, you
Yeah.
have t squared elements.
Yeah. But let me make that precise. Let me make this precise. It's, of course, I mean, I wouldn't talk about it if we couldn't compute this. Right? No, it's there, but let me show you how. Well, this conditional probability, right, can be written as the joint probability O1 to t, x1 to t, divided by the x1 to t joint probability. This is just what Bayes' theorem says. Right? Now, this joint probability is actually there. Let me once more, so just for the fun of it, on top of the fraction here, we have p of x1 times p of O1 given x1 times the product where k ranges from 2 up to t, transition probability, xk given xk minus 1 times emission probability, OK given xk. And this one, I'll just erase it. Oh no, it's still there actually. So here we have p of x1 times v product k equals 2 up to t, p of xk given xk minus 1. Do you see that? Right. So we ask for how could we express this conditional probability? Well, one application of Bayes' theorem tells us that this expression is exactly this expression, but this is the joint probability over all the variables we observe, and this is the joint probability of just the hidden state variables, which is given by that. Now, lo and behold, certain things cancel out, in particular these. So there you go. This ingredient of the marginalized distribution can indeed be expressed, as you said, in terms of the emission probabilities that are part of our hidden Markov model. So, in conclusion, it is indeed possible to compute the probability of a sequence of observations given a hidden Markov model. Yeah.
I have two questions.
Yeah.
First one, in our sum, we have a product of the conditional probability and the higher one, right? So
yeah.
These things aren't really cancelled out. There will be another term which will bring exactly the term.
Yeah, but no, this cancels out, right? I can multiply this back here, then we have it twice, so it cancels out once. There's no problem.
Yeah. And the other question is, if we have the form of the joint probability here on the denominator, why then in our first equation we used joint probability, then we moved to the conditional probability, and then computed these two where we could just directly use the joint probabilities.
No, we cannot, because when we okay, so what I did here is I demonstrated to you that we can answer the problem we are dealing with. And the problem we are dealing with is to compute, I'll just plug it in here, to compute this. And we write it as P of O1. This is the problem. This is, we want to attach a number to this probability.
Yeah, then we use marginalization, right?
Yeah.
And then we came to the joint probability,
yeah.
right? So, and here in the denominator we have exactly the joint probability.
Yeah.
The question is, why did we move to the conditional probability part and then came back one step again?
This is voodoo. I only did it to show you. This cannot be computed directly.
Yeah.
We don't know this. It is not there. It is not, we do not have these numbers. So we have to reduce it to something we are given. And this is what I demonstrate, that it is possible.
Yeah.
That by a crazy idea, oh, let's pretend this is the result of marginalizing out over all the states. Right? That if we were to say that this is the result of having marginalized over all the states, well then, once we marginalize over all the states, all of a sudden there's no axis in here. Right? But by marginalizing, we introduce them. And once we introduce them, we can do algebraic mumbo-jumbo. No, it's true. This is mumbo-jumbo. Right? And by doing this mumbo-jumbo, we can reduce this or transfer this into stuff that we are given. And this is the only thing I wanted to show you. We can compute this. There are no x's in here. There are not. But by marginalizing them out, we can sort of reintroduce them, and then we have to move the more extended form of our problem into a form where we actually see, oh yeah, now we are dealing with many parameters that are actually given in our model. So we can now, instead of P of O1 x1, I could insert a number here, because it's given in my trained model. And instead of transition from xk to xk minus x, I can insert a number here, and then hit return, and whoop, a number for this will be produced. That's all. That's all. And I can sympathize with you, because when I was a student, and this is so funny, because now I consider your, no offense, question very silly, but when I was a student, these things drove me nuts. Why would anybody do this? Seriously, I can totally see your question, because first we do something, then we replace it, then we cancel it, and why have we done it in the first place?
Maybe I was not, my original question was,
yeah.
why do we use, at one step there you have used bias theory.
Yeah.
Why did you do that if you have the form of the joint probability directly here?
Well, but this is just one ingredient. There was this other one. I'm not going to write down this marginalization thing again, but
yeah, please don't. Yeah.
No, seriously, I too once thought, like, why are they doing this? Why make it so complicated and simplify it again? Why in the first place? But the reason of this exercise is I had to show you that we can really compute this given the numbers we have. And to see that we can do this, we have to blow it up and then do lots of stuff. But all of a sudden it turns out, oh yeah, there it is. Right? But I said this is the naive approach. Nobody in their right mind would do this. Nobody in their right mind would do this. Because we had this sum over all possible sequences of states, right? And we are dealing with m states and sequences of length t. Sequences of length t. So what we just did, if we were to compute the probability of a sequence of observations using this idea of marginalization, would lead to efforts the order of m raised to the power of t. M different states, we have a sequence of length t. Each state could be, each state variable could be in any state. And t can be 100. Right? And whenever you see something raised to the power of 100, you know this is impossible. Does not work. I mean, you know, theoretically no problem. Practically absolutely impossible. We'll compute longer than the age of the universe. There's like nothing we can do. So this was just to show that in principle it is possible. And now it's time to reveal the reason we are so interested in conditional independence. And we will now study the forward algorithm. So I said we use the Bauckhage algorithm to train a hidden Markov model, but we'll not look into that because that would totally take us too far afield. We use the Viterbi algorithm to look into what a hidden Markov model actually does and probably tweak it. And we use the forward algorithm to answer our question, like how can we compute this probability of observing a certain sequence of observations? How likely is this sequence of observations given a hidden Markov model? And let's just consider this. We are dealing with the problem of having to compute this. And I say, yeah, we can pretend that we can compute this if we understand this as the result of marginalizing over all states. We have a huge joint distribution, we marginalize half of the variables of this joint distribution, we marginalize them out, that is what remains. Well, instead of marginalizing out so many of them, very theoretically, let me just write it down and then see what I just did. So instead of marginalizing over all x1 up to xt state variables, right now I say, well, this could also be the result if we were to marginalize the joint distribution of the observation in just the last state variable. We don't know if that makes sense yet, but mathematically, theoretically, this is perfectly okay, right? If we sum this probability over all possible values this variable can assume, what remains is this probability. That is what marginalization does. Perfectly okay, no problem here. I could have, of course, chosen any other state variable for this. Right? I have chosen the last one because looking at the sequence here, we see that somehow the last one depends on the previous but last one, which of course depends on the previous but last one, and so on and so forth. So if we sort of try to answer this question with respect to the last one, we know that somehow here there is, if we're talking about this random variable in a very loose sense, we talk about all the previous states. Of course, there is conditional independence, but in order to actually observe this one here, we would have to run through the chain. So what I'm doing now here is I'm considering the joint probability of a given observation and the value of the last state variable. This is stupid, because if we look at this, now there is an xt in there, but apart from that state variable, there is nothing in there we are given. There's no, this here does not have a state transition probability, there is no emission probability, there is no initial state distribution in here, in this expression. And now comes yet another crazy trick. So this is the problem, like we want to compute this one here, right? And I said, we can pretend that the probability of this particular sequence of observations is the result of marginalizing this joint probability over all the values of the last state variable. So let us look into this probability here. I will erase all of this. We look into how we could compute this. Once we know how we can compute this, then of course we can compute this. All right? And here it is. So I'll briefly rewrite it. I'm just changing the order. It's not really important. Probability, joint probability of the last state and a given sequence of observations. We can think of this probability as the result of marginalizing away another random variable. In particular, we might think of this as marginalizing over xt minus 1, ranging from 1 up to mp xt minus 1, or 1 up to t. Makes me crazy, right? Why? Again, marginalization. But mathematically, this is perfectly true. We marginalize away this random variable, and if we have this joint distribution of these three variables, where this last one actually is a very long list of variables, joint distribution of these three things, if we marginalize out the one in the middle, we get this. It's perfectly okay. Let's rewrite it. So, I can write this as the sum where xt ranges from 1 up to m, and now I'll apply Bayes' theorem. I'm sorry. Say OT given xt, and I'll talk about it in a second, xt minus 1, and then O1 up to t minus 1 times p of xt minus 1, O1 up to t minus 1. What I have done here is I have chopped this sequence into two parts. I took away sort of the last element of this sequence, and then I wrote this joint distribution over all these variables in terms of a distribution of the last element of the sequence of observations conditioned on the state, previous state, and the remaining observations. And of course now the second term is this one, right? And I will expand this even further, and I will do it in this line because I need the next one. It's more important than this one here. So what I just erased can be factored further, namely, so this one reoccurs, p of ot, xt minus 1, o up to t minus 1, and now times probability of xt given xt minus 1, o1 up to t minus 1, times, I have to write this one here, probability of xt minus 1 given o1 up to t minus 1, and the final one is the probability o1 up to t minus 1. So this is yet another application of Bayes' theorem, and I applied it to the second factor in what I just erased. Okay? And now we finally see why machine learning people are suckers for conditional independence. Looking at the graphical model, we see that OT only depends on XT. All of this does not count. If we do the math, then it is there, but looking at our model, we know, we can actually ignore this. Looking at our model, we see that the probability of observing a certain state in XT, given XT minus 1 and lots of observation, this does not influence this. Right? So this is conditional independent. And this here, let me write this in another form. I will write this as, again, the joint probability, I can do this, of pxt minus 1 and O1 up to t minus 1. Right? Now I sort of reversed based here. So what we have just seen is that this can be written as the sum where xt minus 1 ranges from 1 up to n. We have to sum over all possible values of this state variable. We are marginalizing it away. P of OT given xt times P of xt given xt minus 1 times P of xt minus 1 and O1 up to t minus 1. And here, finally, we see why we have been studying conditional independence. And at the very beginning, when we began studying, I said, the only reason why we love graphical models and we try to formulate everything in terms of graphical models is that it simplifies inference. And here it finally is. Here it finally, this thing, daunting looking thing, because of our model, actually is as simple as this. Well, simple, in quotation marks. So here, and same goes here, these really complicated things become rather simple because we assume this model structure. And this is once again because of the conditional independence. Independence, right? But we are not done yet. I have to point your eyes to, so we have the joint probability of xt given O1 up to t equals this, this equals this, this by conditional independence equals this, and here we have the joint probability of xt minus 1 given O1 up to t minus 1. There's a recursion. Exactly. Exactly. There is a recursion here. And therefore, I will rename this here. I'll give it a name that is usually used in the literature. I shall call this alpha t of xt. This is just another name for this probability here. And accordingly, this here is alpha t minus 1 of xt minus 1. And as you said correctly, there is a recursion here. And let's use this recursion to have another look at our problem. I will erase all of it. So, therefore, given what we just discussed and having finally discovered the reason and the beauty of looking at conditional independence, therefore, the question we want to answer, namely the probability of observing a certain sequence of data, O1, O2, all the way up to OT, given what we just discussed, well, is the result of marginalizing over the last state variable in our model, P of xt and O1 up to t. So this is it's arbitrary. It's in a sense it's arbitrary. It's not so arbitrary. It's smart to start with the last one. But you know what you marginalize out really depends on experience. This is no problem. And we have just established that this can be written as the sum where I ranges from 1 up to m alpha t of I. And no. Yeah, I should not have erased it, but I need the space. It's indeed this is. Yeah, I could have written x I ranging from, but I don't do that. I'll just I'll just enumerate them now. Right. And let me plug back into this alpha t. What this was. So we have a sum where I ranges from 1 up to m, and this alpha t of I is, as we just saw, another sum, j ranging from 1 up to m, p of ot, given that xt is I, times p of xt equals I, given that xt minus 1 equals j, times alpha t minus 1 of j. This is indeed it. Right? And of course, now we don't need the graphical model anymore. So finally erase it. Every recursion needs an anchor. So what if t is 1? So for t equals 1, we would have that the probability of just observing O1 is given as the sum where I ranges from 1 up to m alpha 1 of I, and this is more simply sum ranges from I up to m. P of x1 is I and O1. And yeah, I'll be precise here. This is this ranges from 1 up to m. P of x1 equals I times P of O1, given that x1 equals I. These are again things we are given in our hidden Markov model. So the recursion is indeed well anchored. And there you have it. So we have found a way of computing the probability of a sequence of data, sequence of observations, and we have found a way of computing it recursively. And in particular, why is this cool? We have dramatically reduced the costs of the problem. Whereas, so we have gone from O of m raised to the t, complexity. This is not a state variance, it's like complexity now. Probably I should call it theta just to make sure that this is not one of our observations. This was the computational complexity of the naive approach. And here we have a double sum ranging over all states. So this is something obviously of the order m square, so of this double sum, but we have to do it t times. Right? For every element in the sequence we have to evaluate this double sum. So this is it. Hmm?
Much better, right?
Much better. So make it, I don't know, for instance, we don't need this anymore. This is like, I mean, really you have to appreciate the fact that this is much better. Say, I don't know, m is 10 and t is 100. This is moderate, right? We have 10 hidden states in our model. Why not? 10 seems to be a good number of abstract states for to describe something. And 100 observations, and come on, 100 observations. In game time, that is 1.5 minutes probably, or even less, right? So 100 game ticks. So with the first one, we have that the naive would be 10 raised to the power of 100, which is older than the age of the universe. And here we would have, it's 10 squared times 100, and this is, as you said, 10,000. So there you have it. And to summarize this, we now know how to use hidden Markov models to recognize temporal patterns. And in particular, it can be of varying lengths and whatever. We did not talk about how to train hidden Markov models. That is slightly a different beast altogether. We did not talk about inspection of hidden Markov models. That is also, we happily assumed we are given a hidden Markov model. And then we saw that once we are given a hidden Markov model, it is indeed possible to compute the probability of observing a certain sequence of data. And this is, 10,000 computations, and that is, lots of products in here. This is still not really cheap, but on modern computers, your iPhone can do speech recognition. And whenever you have speech recognition, you can rest assured that there is a hidden Markov model running. Where this observation would be lots of audio recordings, right? Features that are being computed out of audio recordings. And the states are words. The latent hidden states are words, and once you recognize the words, you can try to recognize sentences. So, this can be done, and it is being done in practice these days. There you go. Final thing, once more, and this can only be done, seriously, I'm not kidding, because of the particularly simple conditional independence structure of the model we use to represent behavior. Now, that wraps up what we have been talking about for the last couple of lectures, even weeks. Are there any questions?
This looks really promising.
Yeah.
Do people really use it now, or
In games,
yes?
I am not aware of any instance where this is being used. There might. I have to check it. I don't know. It is promising. It definitely is, and it is not that difficult. But do not forget that we spent 3 weeks on this. So this is the result of 3 weeks of work, right? And imagine you were a game programmer, coming fresh out of university, I don't know, probably not having taken a course like this, And then somebody says, oh, here's this book on hidden Markov models. I heard this is great stuff. Read it and implement it. So this is the result of 3 weeks of work of ours. And after 3 weeks, everything falls into place. 3 weeks is a luxury in industry. Yeah. So it's very promising. Is it being used? I'm not really aware of any prominent cases. Why isn't it used? It's too complicated. But it's not that complicated. So, yeah. Any other questions? All right. If not, then this concludes our lecture because next Thursday is the exam. Thank you very much.